Hello and welcome to GorillaPhysics Live, and hopefully I've sorted out the audio from yesterday. Thank you very much for watching if you did yesterday, but there was an issue with the audio, so hopefully this is much better. Let me know in the comments if it's not, and I'll stop and sort it out. But you should be able to hear me loud and clear. So this week on GorillaPhysics we're going to be looking forward to those exams which are starting again or continuing if you're a GCSE, and I hope they've been going well so far. Or if you're A-level and you're doing the full A-levels, then they're kind of starting on the Monday back. So the first paper of all your A-levels are on the Monday back. And in today's GorillaPhysics Live, we've got several things for you. We've got some derivations, and we've got some tips on how to study during this half term. So the main kind of things I'm going to go through today is derivations, and I've got loads of examples for them, some that I've been asked for and some that I've not. This half term, some of the other things that I'm going to go through are going to be maybe some of the hardest parts in the GCSE, and how to use your knowledge to solve the problems. So these new GCSEs have got some really tricky bits, and that's going to be useful to you if you're doing A-level, because the trickiest bits in new GCSE will probably be the easiest bits on the AS, so stick around for that even if you are. And we're going to have I think I'm going to run through all of the practicals in the Edexcel A-level. Now that's the exam board I mainly do, is Edexcel A-level, but if you do other exam boards, then there's going to be loads of stuff in those that are going to be really useful to you, so stick around for that as well. So that's probably later on in the week. Also, I thought decoding the 6-mark question. There's loads of other things that people have been dropping in and leaving comments and asking for, and I'll hope to cover more of that. So do just let me know. So derivations today, and well, we're going to get to that just after a couple of other things. Okay, so firstly, let's talk about how to study during the half term. So at half term then, it's really tricky because you're going to need to be intense at some of the points, and I think that's a really important thing, is being intense during the half term. And what I suggest you do is you take the week, today is Monday, okay, and you split it down into 3 sessions, just like the 3 sessions at school, and you have yourself a session which is not intense, so you're not doing anything that's really serious during 1 session per day. So maybe these are like 3-3-hour sessions, morning, afternoon and evening. And I think that's a really good way to think about your study. What I mean by working intense, I mean doing exam questions, doing things like these derivations, doing questions out of the book, working on the things that really, that really challenge you, not just the memory work. And maybe in that kind of Saturday and Sunday, especially the Sunday, which is the day before this Monday exam, that's when you're just doing the memory stuff. This is going to be quite a chilled out day, because you've kind of backed up yourself by having those intense study periods. Okay, so that would be my sort of suggestion to you. Now I'll be here a couple of times during the evenings. I'm probably not going to be able to do tomorrow or Wednesday, but Thursday I should be back with some more bits and bobs, and that largely depends on you. So let me know what it is that you're going to be after for those periods. Okay, I hope that was useful to you, just sort of straight off the bat, how to kind of plan out this week. It shouldn't be all kind of really intense study, but you do need to still work at that high taxonomy. You don't just work on kind of memory work, you work at a high taxonomy. And one of the things that's really, really important, in fact I think is probably the most important thing in the A-level, is going to be derivations. So we've done revising during a half term, but I think possibly derivations is the most important skill. And I can remember when I was doing A-level myself, I can remember really just sitting struggling through pages of derivations, and that's what I'm going to walk you through now. Before I do that though, I want to say Ramadan Mubarak to a lot of you, well, to all of you actually, but a little tip about studying during the half term, and it is Ramadan at the minute for you. Well, okay, I think the middle part of the day is where you have to take your break and probably get yourself a little nap. And actually, I saw a video just the other day by Mr Mahmood, who, if you're GCSE and studying GCSE maths, which if you're GCSE, you're doing GCSE maths, then he's got a channel with loads of maths tips, but he's also done a video, which the link's in the description, to how to study in how to study in Ramadan, and he's saying basically that you need to kind of organise your study around your meal times. So basically you get up early, have the meal during dark hours, do some study then, or that's going to be your first session and that's going to be your first exam, so that's okay. Then after school time, okay, and still when you're not at school during half term, still take that break and have a nap at about sort of 4 o'clock, and do that until maybe 7, get up a bit early from that, and then have a little bit of study time before that iftar, before the evening meal, and then a bit of study after. And he also reminded you to be eating healthily. So that's the kind of main principle. Make sure you eat healthy, lots of carbs and things to give you energy throughout that daytime, okay, because in the exam period you're still going to need that good quality energy there. The other thing I just want to talk about before, actually I'm going to have a little look at the chat just before I go into derivations, okay, and I hope this is really useful to you. There's some derivations that have been requested, there's some from every exam board, and I've got a tip for how to find derivations and which one's going to be most useful for you, for your A-level. And before I do that, I just want to talk about my journey to 10k subscribers. Now I want to get to 10k subscribers because that way I will get what's called a community tab, and I'll be able to put out more information, kind of not just as video uploads, not just as live feeds, and I'll be able to put out sort of post you to other videos that I like, for example Mr Mahmood's video there, and hopefully that will make it more useful. Now I want to be really useful to as many people as possible. I also have now a Patreon page as well, which is linked up down in the description as well. If you're interested, then I really want to create with Patreon a kind of small community around my channel that's going to help me develop that channel in the future. So it'll be a place where I'll ask you, what do you think of this, what do you think of this, because I've got really big plans for next year, really big plans, and I want to know what kind of a few people who are highly engaged viewers that I've got, what do they think about what I'm planning on doing with my channel. Alright, so I'm going to jump into the derivations next, okay. Okay, so what do I mean by derivations? What do I mean by derivations? Oh, I said I'd do chat first. No, okay, I'll do a couple of derivations. I'll do 3, and then I will have a look through the chat. Maybe there'll be people saying I don't know what you meant by that. Okay, but what is a derivation and why is it important in A-level physics? Well, if you're GCSE, by the way, stick around. I'm going to be talking about some of the hardest bits in GCSE, but really this is useful. It's a really important skill. It's one of the core skills in physics. So if you're GCSE, stick around for this. Okay, well, a derivation is like one of those questions at GCSE where you have to do 2 calculations to get a right answer. But instead of doing 2 calculations, we're going to take 2 equations, or even more equations, and we're going to turn them into 1 equation. And that means that essentially you've done the 2 calculations within your algebra. Okay, so I'm going to do 2 sort of pretty straightforward ones, starting with the derivation of Newton's second law, which you probably know as this: a resultant force is a mass times acceleration, and how that gets turned into a resultant force is equal to a change in momentum over time, a rate of change of momentum. Okay, so it's all about the definition of this A here, acceleration. So what is another equation that we know for acceleration? An acceleration is a change in velocity over time. Well, what's a change in velocity then? Well, a change in velocity is v minus u, the final velocity, take away the initial velocity, over time. So now if we put that expression for A into F equals ma instead of A, we're going to get a new equation for a resultant force. Okay, I hope that makes sense. So that expression, A equals this, I'll put that instead of A. And then, as you know, when you've got a bracket, let's expand the bracket to make it a bit neater. So we end up with this, mv minus mu over t. So this is the final momentum, this is the initial momentum, so all of this equals a change in momentum over time. So we've derived another way of calculating a force, or another way of explaining force, and it turns out to be really useful in explaining, especially at GCSE, car safety features. But anything where we're talking about how we're going to limit a force, we need to think about ways of limiting the change of momentum or increasing the time taken. Okay, so that's a pretty straightforward one. Now, another straightforward one is how do we derive rules for resistors in series and in parallel? Okay, so I'll do resistors in series first, and it's all about understanding all of our kind of circuit problems toolbox, which are Kirchhoff's laws and also Ohm's law. So I'm going to start off with resistors in series. Okay, well, what do we know from Kirchhoff's laws about resistors in series? We know that the kind of supplied voltage, let's say they call it the total voltage, is equal to the sum of the voltages across the other resistors. So this is like how potential dividers work, right? We also know in a series circuit that the current everywhere, the current through the battery is equal to the current through the first resistor, equal to the current through the second, equal to the current through the third. So all the currents are equal. And we know that Ohm's law is the case everywhere in that circuit, V equals IR. So what we can do then is we can put in this into this equation instead of these V's, all right? So the current through the, through the supply is equal to multiplied by the resistance of the supply, of the whole circuit I should say, is equal to the current through the first resistor times the first resistance plus current times the second one plus current times the third one. So I've just basically subbed in this instead of all the different V's, and the R corresponds to the resistances rather than just a random resistance, right? But we also know that all of the currents are equal. So this current is equal to this current is equal to this current is equal to this current, so we can just cancel them through. And we get our equation for resistances in series. R total is equal to R1 plus R2 plus R3, so they just add up. Okay, what about in parallel? We'll have to find another rule for the same situation in parallel. So resistors in parallel. Okay, well, what do we know about currents in parallel? Well, the current through the supply is equal to the current in the first branch plus the current in the second branch plus the current in the third, and so on. And we also know that the voltage from the supply is equal to the voltage in the first branch, which is equal to the voltage in the second branch, and so on. And we also know that Ohm's law is the case. Okay, laws are always the same everywhere. So rearrange that for I gives you V over R. Okay, and now knowing that V's are all the same, we can just plug this in instead of our currents. This is the total current here. First resistor, current through the second resistor, current through the third resistor, which is just the same thing as above. And we know these are all the same, so we get our expression for calculating resistances in parallel, which is this. 2. So essentially, if you want to know the total resistance of a parallel circuit, you sum the reciprocals to give you the reciprocal of the total resistance. Hope that makes sense so far. That is actually something which is mentioned specifically on a lot of available specifications. I know it's mentioned specifically on the LXL spec, which is the one I do. Know how to derive the equations for resistors in series and parallel. So actually they could ask you to do this in the exam. Okay, and you would need to get that from those first principles, those two laws, and get that. So it's a very, very important thing. Now I suggest that is something you do to study during those intense periods this half term, is actually look through your specification, actually just get a PDF copy up in a program on your computer and find in there, Control F, or find all of the mentions of the word derive. Okay, and then from that work through and check you can do all of those derivations. Okay, now actually that was something somebody mentioned to me. Somebody said, I've been looking through the spec, I've been looking through my specification, and this is from the Educas specification, and it has this specification point. I said, well, this is the one part, the one derivation I can find that I'm not sure about. So I'm going to go through this one. It's derivation of an equation for what we call the critical density of the universe, should the universe be flat. Okay, if the universe was to expand to a certain point and then just stop expanding, then this would be the density of it. Okay, so how do we work that out? Well, okay, there's lots of clues. Okay, so I'm going to take you through that and where we can get from our other equations on our equation sheet to figure out how to get to this expression. They've told you in the spec that you're going to need to do this. You need to be able to do this, so you better blooming well be able to do this. Now, in most specs, there's a spec point in there somewhere that says that you can derive anything they're going to ask you from first principles. So be aware this is an important skill. They could give you a few things and talk about how to derive something and expect you to be able to do that in the paper. So here's our target. The density of the universe, the critical density of the universe, is equal to 3h0 squared, and that's the Hubble's law constant, that's called, the gradient of the Hubble's law graph, over 8 pi big G, which is called the universal constant of gravitation. So there's some clues in here. There's some clues straight away of where you should start. So there's this one here, which is Hubble's law. So let's go ahead and write down Hubble's law. And there's also this one here, big G. Big G. The universal constant of gravitation. And where do you find that? You find that in Newton's law of universal gravitation. Okay, constant universal gravitation, the big mass, the kind of Earth in a lot of cases, the little mass, the kind of satellite of Earth in a lot of cases, and the distance between them squared. Right. Okay, now here's a trick for a lot of derivations. We're sometimes going to think about making energy equal, okay, and we're sometimes going to think about making forces equal. The two kind of really common things. Okay, now this is quite a tricky one, okay, but we're going to have to take a leap that actually it's energy equals energy. Right, now we're going to have to think about that universe as it's kind of accelerating, as it's kind of moving away from the centre of the universe. Now how fast would it have to be going to get away, to expand forever? Okay, well, it would have to have enough energy to get away from that gravitational field. So we're going to actually use energy analysis to do this derivation. So we're going to actually make a kind of kinetic energy equal to a potential energy. And what are our two energies? Well, kinetic energy is the energy of the galaxy as it's moving away, and we've got kinetic energy equation there. And the energy of the galaxy at any given point is mgh, right, or for short FD. Now if you think about that, an energy at any point, a work done, is a force times a distance. This is a force, so multiplied by a distance r, then we can turn this equation into G capital M over capital M little m over r. Okay, I hope that made sense there. This is just this force multiplied by a distance to give us an energy. So at escape velocity, at a kind of critical density whereby it doesn't escape, it just kind of stops, then these two energies are equal. And that is the whole premise for the rest of the derivation here. So here we go into thinking about what else we can sub in. So big M is the mass of the universe. Now presuming the universe is spherical, then the mass of the universe would be 4 over 3, 4/3 pi r cubed times by this critical density that we're talking about. So I can put that in instead of this. Now what about V? Okay, well V is given to us by Hubble's law. So V is the speed that the galaxy would be going, which is given to us by h0, and what d is that? What distance is it? Well, that distance is the same distance that we're talking about, r. So what we're going to do next is we're going to put these two expressions into this main equation. So there we go, half m h0 r squared equals g 4/3 pi r cubed critical density little m over r. Okay, now I've got some tidying up to do. Okay, I can expand this bracket, I can cancel these m's straight away, they just go, doesn't matter about the actual mass of that galaxy because the algebra tells us so. And I can do something with this r here, can't I? I can make that r squared and cancel that r. And I need to expand that bracket, so I'm going to do that on the next line. I can also times both sides by 2, that'll be quite a neat little step as well. So h0 squared r squared equals g 8 pi density over 3, because I haven't changed that 3 there. And now I'm only really one step away from my final result that I'm after. I just need to make it all equal to the critical density. So that's just rearranging then, multiplied by 3. I missed one thing off here. R squared needs to be copied down there, but now I can just cancel those. See that one? And now just multiply both sides by 3, 3h0 squared, and divide both sides by 8 pi g, and that gives me the critical density. Okay, that is a long-winded one. That's a tricky one. Okay, I'm going to go through some more. I'm going to have a quick look at the chat just now, see if there's anything I can help you out with specifically. Also gives me a little break, because this is what I'm talking about working intensely. I can remember very, very well sitting and working through pages of derivations to check that I could do those derivations, what they're expecting me to be able to do in the exam. Okay, so that is something that I really, really think that you should do. Okay, let's go and have a look at the chat then. The earth is flat. It's not flat like flat, it's flat like not going to expand. Good evening, yeah, I hope that was helpful to you. I do need a haircut, that is correct, okay, but actually you're looking at a really expensive haircut. It's just had a little bit of time. Hey, it's called GorillaPhysics, what do you expect? Whole topic summary vids. Yeah, I could do. I'll think about that. I don't know whether I'm quite going to get time. If there's any specific topic, then I sort of go through a kind of summary of them. I do have loads of videos. I've got a playlist for each kind of topic in GCSE and A-level on my channel and on my website, so if you want to check those out. Yeah, Lane, it is kind of yesterday's live stream, but as you know, yesterday's live stream was pretty much a bit of a joke. But I'm going to go on to, the audio was pretty bad. I'm going to go on to do some more derivations, which is what I plan to do tonight. As I said, I'd love to do every single night this half term for you. I'm hoping evening time is a good time for you. Maybe it's not a good time for you, but I think I'm going to get more people watching if I stream in the evenings, because you're young people and you all believe that you work best at night, which is not true. Okay, actually get up in the mornings and probably work at times when school is going to be on. Don't this half term spend loads of time in bed, and you have to get your routine back because your exams are going to be in the morning, so you need to be ready for that. How important is it to study over summer? It is and it isn't. What I would do is I would get excited over summer. All right, I would just kind of maybe get a book. There's like Hawkins' book or something like that, and read that. Maybe get the Equations That Change the World kind of book. Don't slave at it over summer. Just try and get yourself like passionate and make sure that you find out why it is that you want to do physics at A-level over summer. Yeah, does that make sense? How do you derive Stokes' law equation? Yeah, that's a good one. I've never actually seen that derivation done. So the other place to look for derivations that kind of commonly come up is your specification, but also past papers. So look at past paper mark scheme, but look through common derivations. And one of them that I'm going to show you in a moment comes up all the time in an Excel derivation. So let's do that in a second. AQA A-Level, the best people for AQA A-Level are going to be A-Level Physics Online, and also Science Shorts has done some really good run-throughs of exam papers, so that's really good. Yeah, so I'm going to talk about 6 markers in the next one. Yeah, don't think of them as being 6 markers, think of them about level of response questions, because they're not all going to be worth 6 marks, okay? And all you need to really think about is plan first, look through little bits, look for the clues, and use that to structure your paragraphs, and then write in paragraphs. Okay, that's the best tip that I can give for 6 marks. But it's one of the things I'm planning on doing later in the week. I'll do how to do level of response questions. Yeah, definitely you got to look for the old spec stuff. You've got to use the old spec stuff, because there's not really enough new spec stuff out there. There is very good crossover. I agree with that, Lindsay. Yeah, absolutely. There is loads of stuff. The A-level physics wasn't changed that much, because a lot of the other kind of sciences and other kind of exams had to improve really, because the government thought they weren't hard enough. But A-level physics, we already knew it was hard enough. It's a little bit kind of cheeky, but I think I've seen a bigger change in chemistry A-level, biology A-level, in terms of the demands of them than I have in terms of physics. Most of the stuff is the same. There's a few bits that are new. They just kind of I think they just put more into A-level physics, so there's a bit more for you to learn. And actually, I think, you're going to hate me, but I think they've made it maybe slightly easier in a lot of ways. Okay, I think there's probably more kind of recall stuff, and recall stuff is easier. Looking at the kind of questions, I think you can figure out how the questions are a bit easier these days. Hello everyone, that's good. Nice to see that, just all say hello, that's good, good. No, it's not flat, Rory's awesome, Lindsay's awesome. Grade boundaries are pretty low since it's compulsory to do physics and other sciences, and many people don't seem to enjoy it. Yeah, I kind of see that. That's really interesting. But I wouldn't rely on the grade boundaries to be pretty low, because you don't go into an exam thinking, oh, I'm going to get 30% and that's going to be good enough for a pass, do you? You think, I'm going to try and get all the marks, so just go and try your best. I know you can do this. Yeah, definitely. The people here, like watching this type of video during their half term, are definitely the people that's going to pay off. Yeah, I'm going to talk about, I don't have angular momentum in a minute, Jake, but I do have some circular motion stuff that's a really common set of derivations. Distance to near and far galaxies, Faraday lens with Fiddy, just be sure. Have you used it? Yeah, the set explanations are really good on my website, so I think that's a really useful thing. And that's great. If you feel confident with the course, then that's really awesome. I take it that's A-level. Yeah, what I would do is maybe just go through my exam playlists. Okay, if you go through my exam playlists, then which are they're linked up below. I've got one for each of the EdXL papers. Have a look, go through them. Make sure that you can tackle them all really confidently, and you get the skills, and you understand. Yeah, I'm going to do Kepler's third law. Planned it. You can get. I've forgotten what I was saying now. I'm going to get on with the derivations in a minute. Yeah, that you can do them all really confident. That you can use your knowledge to solve the problems. Now that's the biggest thing in the A-level exams. Can you use your knowledge? You get all the stuff. Can you solve the problems in the exam? That's the biggest thing. All right. Photoelectric effect. I've got a really good set of videos on quantum. Okay, just check them out in the quantum playlist. Just find in the A-level playlist on the channel. Code's third law is coming up. Okay. SHM. Yeah. Yeah, I think looking at the exam solutions are really good, and that would be the thing that I would be doing on the last couple of days. I would be just looking at as many old mark schemes as I could, not even really worrying about the questions, but looking at the old mark schemes and trying to memorise the kind of things, the ways in which these problems are solved. Okay, pages of derivations, find things. So I've done the first few. I'm going to start with a couple of warm-up ones. Okay, just going to get back to my visualizer now. This is my Patreon levels logo transition there. Okay, let's go for it. Starting with these two beauties, P equals I squared R, which even GCSE will recognise, and V squared over R. Okay, hope you know where they come from. They come from the law about electrical power. I'm not showing you that there. P equals IV. Okay, and Ohm's law. So basically, if we know the current and the resistance, but we don't know the voltage, then we get an equation for power here, which is just simply subbing Ohm's law in as it is into IV. Okay, so that's a pretty straightforward derivation there, and similarly but different for this, if we know the voltage but we don't know the current, and rearrange for current. Sorry. Yep. And we can just plug that into this. And we get V squared over R. Hope that makes sense. That's a nice, simple one, but it is there in the EdXL spec. Derive that equation is something that they're expecting you to be able to do. Okay, so how do we derive? This one is in there as well. An equation for kinetic energy of a non-relativistic particle. p squared over 2m. Well, where's the kind of clue for that? It comes from the standard kinetic energy equation, which actually one of the specifications asks you to derive this equation from first principles, so we'll get to that in a moment, and the definition of momentum, which is mv. Okay, so firstly you take this, put momentum in there, so take one of the mv's, gives you ek equals a half pv. Okay, so one of the mv's, and we've just got one v left over, and then rearrange this for v. Gives you an expression for v, put that in there instead of v, gives you p squared over 2, which is half m. Okay, so they expect you to be able to recognize where that comes from, and a question could be as straightforward as show us where that comes from, derive that equation. Okay, and next one, angular velocity. Okay, so there's an expression, this is the root, I reckon, of most solutions for any circular motion question, mv squared over r. Okay, if we take the m out of that, because f equals ma, then we know that the a equals v squared over r, and they want you to be able to use that to derive an expression for acceleration, which is r omega squared. So it comes from, well, what is omega squared, okay, and what is v. So here's an equation that we can express. So v is omega r. Okay, so if we place that in instead of v, then we get a equals omega r squared over r, which gives us omega squared r, because we just cancelled one of those. And then you can also think about getting time in there as well. If we write an expression for omega, which is defined as 2 pi over the time period, okay, because omega is angular velocity, it's how many radians per second something is doing. So if the time period is doing a full circle or a full SHM cycle, then 2 pi over t gives you this in radians per second. Omega, which is angular velocity in radians per second, so we can sub this in here to give us, I'll just do it the long way around because I'm talking through at the same time. So a is also 4 pi squared r over t. Okay, hope that's a useful one to you. If I don't say otherwise, then it's something that comes up in the edXL spec. Okay, if I say otherwise, then it's something from a different one. So if you don't recognise it, then it's probably from a different one, or something that's just for your interest in working at these high levels. Okay, which is what I'm expecting you to be able to do. So also expressions for energy in a capacitor. They're expecting you to be able to derive these two. Okay, where C is the capacitance, V is the voltage across, work done is the energy stored in the capacitor, and Q is the charge. Okay, and it comes from an equation that you do get given. You get given work done is a half QV, and the definition of capacitance, which is C is Q over V. Okay, I hope you're following that. Okay, so let's just do the first one. We want to get rid of the Q, so rearrange that for Q gives us CV. So put in half CV times V gives us a half CV squared. And similarly, but for this one, we want to get rid of the V, so rearrange for V gives us V equals Q over C. So now put that in there in the first expression, which we got given, which is that one. Put that in instead of V. Okay, and then I hope you're okay with that, Q squared over C. Okay, so that's a pretty straightforward one, but again, there's a spec point that says be able to derive that, so make sure that you can do that. getting to Kepler's law in a little while, but here's another one which is for a charged particle in a magnetic field. Now, a charged particle in a magnetic field, the magnetic field is at right angles to the motion of the charged particle, so it's going to be a centripetal force. Okay, so here's where you're going to use F equals mv squared over r, and another equation for the equation for the force on that charged particle, which is FB QV. And just to make you aware, they're often going to use charge on electron, so in this question it's often starting from something which has got BE in it, and E being the Q in this expression here. So make those two things equal, and you can derive this expression, R equals P over BQ. That's what we want to get to, so let's just make the two things equal. The two forces are one and the same. Okay, cancel one of the V's. mv over r equals bq, and multiply this side, both sides, by r. Well, I want to leave it as r as the subject, don't I? Well, that's just momentum there. Leave r as the subject, so p over bq. Okay, that's a really common one. Again, you're given that equation in the formula sheet in Excel, but they expect you to be able to derive it, so make sure that you can. Derive an expression for this one, gravitational field strength, or G, gravitational acceleration would be as well, in terms of the universal gravitational constant. M1 is the way they refer to the big mass in LXL over r squared. Right, well, where does that come from? That's actually much more straightforward than it seems. The Newton's law of universal gravitation, and the definition of this force, which is a gravity force, which is weight is mg. Okay, so basically to get, and that m incidentally is the little m, is the thing which is being accelerated, so that's that one. So we just have to basically times this force by, or sorry, rather divide this force by m2 to give us g. Follow that? So divide this by this, just cancels that one out. G equals gm1 over r squared. Okay, they're asking you to be able to do that. Now Kepler's law, I'm going to need a bit more paper. Kepler's law simply states that the time period of an orbit, the time of an orbit is squared, is proportional to the radius of that orbit cubed. Okay, now it kind of models orbits as being kind of roughly circular, or we call that the semi-major axis of the orbit as well. Okay, again, it starts from an equation of circular motion, being this one, and making that equal to Newton's law of gravitation. I'm going to go back to the other notation here. Okay, and then we have to put in a definition of v in terms of omega, because that's where we're going to get our time period from. V is omega r, so this is angular velocity, 2 pi over time basically. So let's go ahead and put that in there as well. So sub that in instead of there. So V is 2 pi r over t. Very useful expression to remember. And then I'm just going to sub that in there and tidy up my r's a little bit. I can also at this point cancel my m's, can't I? V squared equals gm over r, put this expression in there, 2 pi r over t, all that squared, equals gm over r. Expand the bracket, 4 pi squared r squared over t squared equals gm over r, times both sides by r and just move the t around. 4 pi squared r cubed equals g m t squared. Now, haven't we actually satisfied Kepler's law anyway, because we've got r cubed and t squared there. All of these other numbers are just constants, okay? But the way it's normally expressed is like this: r cubed equals gm over 4 pi squared t squared. Would that kind of indicate that that is a constant? Hope that one makes sense to you, especially if you were after Kepler's third law. Two more, I think, and then I'm done with derivations. That one actually is in both EDUCAT and the OCR-A syllabus. Okay, I had a look in OCR-B and I didn't find the word derive mentioned in the specification, but I'd be really surprised if they weren't expecting you to be able to derive things, so look out for that. This one is such a useful expression, I'm surprised it's not in more. Okay, power as a force times the speed. Well, it comes from a lot of things. What is a power? Okay, well, a power is a work done over time. What is a work done? Well, it's a force times a distance. Okay, and well, what is a speed? It's a distance over a time. So if we just start with power, put work done over there. Power equals force times distance over time, and then this d over t is just v, so power becomes force times speed. I think that's a really useful expression for a lot of quick calculations. I think I've seen that on all specifications as well. And then the last one that I said was how to derive half mv squared. This one is a bit of a new one on me. Okay, well, it comes from the definition of what kinetic energy is. Well, the kinetic energy given to something is equal to the work that we've done on it. In a kind of ideal world, by energy analysis, is this. And what is a force? A force is a mass times an acceleration. And before you do anything, you need to expand. You need to get to. You want v squared in there, don't you? So you need to rearrange this for a. Using this one, v squared equals u squared plus 2as. U is 0, considering we've accelerated this to this speed v with a constant acceleration. So v squared is 2as. V squared over 2s equals a. Sub this in there for this one here. F equals mv squared over 2s. This in here instead of the force. Okay, so the kinetic energy is mv squared over 2s times d, and this s is the same as that distance, so they cancel. So it gives us ek is a half, which is the over 2 bit, mv squared. That one was new on me today, so that was a quite difficult one. But in OCR-A, they expect you to have to derive that from first principles. First principles in this case being this situation here, where the kinetic energy is gained is equal to the work done on something. Newton's second law being this here, and a equation of motion with v squared and a factor of 2 in it to give you the half. Okay, I hope that makes sense to you all. That's all the derivations. I'm going to spend a little bit of time just going back over to the chat in a moment, and then I'm going to look at the time, see how long I've taken, and tell you if I've got anything else for you tonight. So let's just go back to chat briefly. I'm just going to go back up to where we kind of started. Lots of kind of off the derivations chat, which is absolutely fine as well. Don't mind that at all. good suggestions for different revision guides. Keith Bridgman, is that a YouTube channel? That'd be really interesting. Yeah, if you're doing mechanics in maths, that's really, really useful for your physics as well. Yes, you should chill out a little bit during your revision time, definitely. Yes, Lindsay, you do seem really well prepared actually for the exam. There's kind of challenges that I've put out there, you seem to have really good solutions for. I was wondering if you were a physics teacher actually, by the way that you kind of discuss physics, the precision that you do with that. It's really, really good. What's the best way to revise science? Tricky one. Questions, definitely questions, but not just exam questions. There's a difference between the questions in the textbooks and the exam questions. Okay, the questions in the textbooks take you through all the kind of different possibilities and the kind of building up the kind of skills that you need to do that. It's not really about revision, but it's about the way that you tackle things. I think a lot of people revise the kind of knowledge and they get to the exam and they find that there isn't the kind of questions they're expecting. They're not just asking them to recall some facts or anything like that, and all the stuff that they've revised seems a bit kind of useless regarding what it is that they're being asked. And the thing is that they're not understanding that they're just a set of problems. The questions are a set of problems, and your knowledge and understanding that you've revised can be used to solve the problems. Okay, so I think that's why people struggle with science, in my opinion. It's not that they're not working on it, it's not that they don't understand what they're being told, it's just that they don't understand the kind of problem solving they have to go through. Yeah, power, force times speed is very useful. Okay. Great if you're here in year 9. That's wonderful to hear, okay, because if you've just watched that video about A-level derivations, then by year 9 hopefully they're going to seem nice and easy to you. Okay, that's me for now. I'm going to, what I think I might do, I want to go through some of the hardest things in GCSE. I'm going to drop this feed just to have myself a little break, and then I'm going to come back and I'm going to go through about 15 minutes, some of the hardest things in the new GCSE. Now if you're A-level, I suggest you come and watch that anyway, because some of the hardest things in the new GCSE might well be some of the kind of easy parts of the A-level. So I'll drop this feed, I'm going to go check on my wife and Florence, check that everything's okay there. Have myself a little break, maybe about 15 minutes, and I'll come back with some more stuff, maybe mostly geared to the GCSE. Okay, so thanks very much for watching. I hope it's been a useful live feed for you. I'll be back in the not too distant future, so keep an eye out. If you haven't subbed up already, then do that. Make sure you've got notifications, all of those good things. Check out the playlist that I've got for the EdXL exams. Even if you're not doing EdXL, go through those. If you're doing like CIE or AQA or Educas or any of the others, there are loads of other great YouTubers out there, but I suggest you watch videos that aren't just for your syllabus so that you get used to solving the problems, because physics is universal. It's not, don't just study your syllabus, study physics so that you can be well equipped to solve those problems in the exams. Alright, thank you very much for watching and catch you again soon.